So let us quickly revisit the concept of induced EMF and how these induced EMF can be altered, or rather their induced EMF wave shape can be altered using two factors, namely the breadth or distribution factor, and another one is it's like pitch factor. Generally it is denoted by KB or KD, and this one is denoted by KP, and together they form KW, known as winding factor. Now here one interesting things to note before I start the technical discussion. Let us recap it quickly what I told you, that flux density waveform, just recap, flux density waveform, most of the cases it is having half wave symmetry, periodic but non-sinusoidal in nature. Time variation of the induced EMF exactly follows the space angle variation of the flux density waveform flux density waveform. This is true for full pitch concentrated coil. Now we have developed two cases, like just two factors. So for concentrated coil they mimics it. However, for distributed, while you distribute your winding, you cannot keep it in your mind that like altering winding configuration by means replacing concentrated winding by the distributed one, or using pitch or fractional pitch. Altering winding configuration does not alter flux density, space distribution. You may find it very easy and boring at this moment, but if you forget all this, then later on you will find yourself in a soup. So don't ever think about forgetting all this if you at all want to understand and excel in this subject. Now the fourth point that is also very important, like fourth point, what is that fourth? Yeah, fourth point is that this winding modification or alteration to a new configuration results in time variation induced waveform should waveform that it become more sinusoidal. Point number 5. However, any winding manipulation or any winding redesign always costs you in terms of like whenever you change the winding, your machine voltage rating or induced EMF rating will fall, right? So that is a case. You should not forget that if you change, it will fall. Now see what is the interesting things here, that for non-sinusoidal, your flux density, what we can write that for non-sinusoidal flux, we can write B is equal to, our flux is like, here we are considering that both flux, even harmonics and odd harmonics are present. Don't get confused with the order of the harmonics with the symmetry of the harmonics. At any point alpha, we can, the flux density can be written in this way. At end it is and the second part, that is V1 double dash cos alpha plus V3 double dash cos 3 alpha plus B5 double dash cos 5 alpha plus Br double dash cos R alpha. It's like that. So combining them, you can write it like it is this B alpha is equal to B1 sin alpha plus phi 1 Now, what are these B1 or generally say BR? These BR are as expected, and this angle is right. So you can easily understand that what type of means field distribution you can get here. Now one more thing that is kind of like interesting to note, that your what would happen to your individual flux. Like if this is the case, then for individual EMF will be how much? EMF will be right. And how to get phi r? Phi r, you have to use that formula, that is phi r is equal to, or you can simplify it like 4.44 What is phi r? Phi r is okay. So this is our phi r, and we'll get the values. And how we can find out the resultant EMF? Resultant EMF is like resultant phase EMF. And what about resultant line EMF? That is like, suppose if you connect here, you have to apply the same consideration of transformer. Like in case of transformer, what we had, if it is star connected, then no third harmonic current can be present there in the line. So it should be like that. E3 should not be present at line expression. This is for star connected grounded neutral three phase transformer. Now
another the different types of transformer we can have, or simply this form of like our machine. The one thing that is what I was discussing and could not tell you the answer at the beginning, that obviously the area need to be, area is means a big issue where if you see this, then this area that is formed by this rectangle pi dl, it is very important. Why important? Because you can see that this pi dl, the flux is perpendicular to this, and therefore this is the effective area which is responsible for your EMF production. However, what we will see that if we where should we use a machine with means high value of shaft length, or where we should use a machine with larger dia. So one obvious answer is that we can have actually in power systems we have two different types of turbine mechanism. The turbine is not under the purview of the course, but we have thermal power, means if you talk about the conventional energy, then it is thermal power. So thermal power, we see that thermal power turbines are high speed. So if you in case if you see that you need to make sure this pi dl should be means considerable area should be offered to your flux, because flux density is dependent, maximum value of flux density is dependent by the material, not by any other thing. So once you fix up your material, which one you are going to use for your machine construction, then your BM is fixed. So you have to work with your this. Now if you want to make this constant, now think about it. If you use larger D, then what would happen? The machine will have a larger dia, right? This larger dia, now you can see that, just 1 minute. So if this is R and this one is rotating at a speed of omega, means angular speed of omega, then what is force? Centrifugal force experienced by any conductor will be how much? That will be, if the conductor mass is m, it will be m omega square r. So increasing d will obviously increase this r, and for same speed what you will have more centrifugal force. Now where your machine itself is having a high value of omega, like high speed thermal turbine, in that case if you use it, then what will happen? This will means like the machine rotating part will experience a very high value of centrifugal force, which is not at all desirable. So in case of this kind of machine, like that is associated with high speed prime mover like thermal turbines, we use a structure of the machine that is having more axial length and less dia. So undoubtedly it's a cylinder. So what we do, we use something that is having more axial length. What I am trying to say this is our cylinder. So now in this cylinder, this means lateral area of the cylinder is how much? Pi dl. So if you have Bm constant, then if you want more flux, then these the product dl should also, you have to increase that dl product. However, for a high speed machine, having a larger d is problematic. So what we need, so we should have, or we should means use a machine with so obvious question is will come in our mind that if increasing D is having such a negative effect in terms of mechanical force experienced by our rotating assembly of our machine or rotating parts of our machine, why should we go for large D? Why not let us see, this time you have to be very means sensitive, or means you have to sensibly decide that whether we will go for a larger dia or smaller dia, and obviously the length consideration will follow immediately, because if you want a certain amount of flux, obviously either you have to increase the dia or you have to increase the length for a given machine. However, for high speed machine we cannot use a larger dia. The dia must be of moderate size, the diameter of the cylinder or cylindrical stator, but axial length we can increase the axial length, there is no harm. Now this just whatever we have discussed at this moment, it may gives you an impression that there is no harm. We can use a very small cylinder, just like a means machine. A stator can look like a pencil of a very long axial length, but why we cannot just squeeze the dia below certain limit? Think about it. If you what is your dia actually? What is the physical significance of your dia? Now, if we take the front view of your machine, it is like okay. Here we can get this is the front view of the machine.
So this is the front view of the machine. If you are not able to see it, then just now this is the center. This is the dia. Sorry, this is the radius, and the total is the dia. So what we can see that if we switch, what is there in this? Here you are having slots, right? You are having slots here, here, here. Now you must have certain plan in your mind that I need to put this many slots there along the periphery or on the lateral area of that machine. I need to place this many conductors. So this many conductors also, like, it is pointless that if you claim that I will reduce the interslot angle as well as the slot width. What you will get by doing so, that it will become extremely difficult for you even with a machine to place your winding correctly if you just keep on squeezing this slot width. Similarly, interslot angle means between this, if this is the iron part, if you try to squeeze this portion where there is no conductor, but if you squeeze it below certain limit, then what will happen? This will become extremely fragile and mechanical strength will become very weak. So you can't do that. So in a nutshell, what we can say that if we want a certain number of conductors to be placed, then we have to give a certain number of die. Now obviously one question can comes in your mind, that why do we need so many conductors? Remember, whether if you are looking for a higher rating machine, there are two ways to increase the rating. One is by increasing the voltage level. So obvious choice of your voltage, as flux is a part of voltage. By increasing the flux, you can increase the voltage. But at the same time, if you reduce that number of conductors, basically reduce means if you switch the diameter, then basically you will gradually you will realize that you are not able to place all the conductor slot across your machine periphery. So what you need to do, if you want to cut down the dia, you have to cut down the number of slots present on that surface, on the lateral surface of the cylindrical stator. So if it becomes your practice, then suddenly after a certain time you will have a very small number of stator slots present with you. Now you may argue that what is wrong with that? We can have this small number of stator slot. Say we can have six slots, right? 6 slots, one conductor in each. Now do remember one thing, that first of all you yourself has spoiled the flexibility of the machine by making it a concentrated winding, because if you take 6 slots and 3 phase, then obviously it becomes a concentrated winding. You cannot, and also if you consider it as a single layer, then distribution of that winding is not possible. So whatever advantages or attenuation to the harmonics you could offer using your distribution factor, that is gone. Now you think about one
question and let me know that can we have short pitch coil for single layer winding? Think about it. Anyway, let us consider that we have this one, but still you will not be surprised to understand that what you will have, like if you keep on squeezing this dia, the number of slots will be reduced, and obviously that will not only the number of slots but the number of means, in a nutshell you can understand it in this way, that number of slot reduction is directly proportional to the number of, what I am trying to say, let me just try to explain this pictorially. Like if with this present dia we have 3 slots allocated to same phase group, it is a distributed, I am just giving you a rough idea. Now due to a smaller one, say when you have this, then you can only place one slot with same width. So one slot will be occupied by that particular phase conductor. So previously you had 3 conductors for carrying certain amount of current, and now you are having only one conductor. So obviously the current carrying ability of your machine will be less in compared to the previous configuration with higher dia, because higher dia gives us a scope to like adjust more conductors on it, more slots can be, more group can be present on that lateral surface, and accordingly you can place more conductors. Now if you think that okay, so more conductors can be present. Now yeah, so we cannot switch the dia below certain limit. However, if you now have a machine with now increase, if you have a very large number of slots due to certain reason, or you want to design something which having more number of poles, so what should you do? Here one important formula you should not forget, that is F is equal to NSP by 2. So in case of thermal turbine that is having high speed, NS is very high, P is small. Now NSP remains constant. If you are looking for numerical examples, this is for fundamental. We can write it like in terms of RPM. We can write if our machine speed is 3000 RPM and pole is 2, then it is 120. So what you will get 50 Hz. Now if you have a machine with say 10 poles, then what you will have here? You will have, if you are still looking for 50, then you should arrange this one in such a way that this produce 50, like it will be just a minute, how to get 50, like for 3000 we are getting so here it should be, the number of poles is now 10 and
these should be, we need just 5. So yeah, we are right. This one was n rpm, and this is number of pole. Now this is number of pole, this is number of n rpm. So one thing we can see that if we want to maintain constant frequency, then for high speed we need less number of poles, and for low speed we need many poles. Or now obviously whenever you are talking about poles also, see, your machine is like a hollow cylinder, and it is means even if you consider it's a cylindrical or salient pole, the poles you cannot place them like 10 poles cannot be placed in over the same lateral area where you can successfully or means very conveniently place 2 poles. The angular span always remains same, that is mechanically 360 degree. There is no change. But when you increase D, obviously your lateral area increase, lateral area of the cylinder increase. And when you need placement of higher number of poles, obviously you need more lateral area. And when more lateral area you need, then what you will have, you have to reduce the speed of the machine also. Like you cannot have, and there is a blessing in disguise, our hydro turbines are very low speed machine, and due to that hydro turbine low speed we can use this. And for hydro turbine obviously it is meaningless to use such huge length L, because using huge L is also not advantageous always. So here what we will do, we will squeeze the cylinder along its axis, means axial length, and we will means make the dia bigger for low speed machine. So now I hope it gives you some sense that what is the means where to select D, large D, small d. So let me just write the conclusion of this discussion. Conclusion is that high speed thermal prime mover are cylindrical shape, rotor a considerable axial length and small diameter is preferred for low speed hydro turbine projected pole larger dia, small or having a shorter axial length, shorter axial length is preferred, right? So you get some idea. Obviously D and L, both of them affect our induced EMF, but we cannot select them out of bound or at our own free will. Anyway, back to business where all these discussions started.
like here. So this is the expression of EMF. You should keep it in your mind. Now we will investigate one interesting things that is known as tooth ripple. What is that? Let me explain. So now we will discuss our topic is tooth ripples. So what is tooth ripples like? Like if I try to draw means picture after surface development. So this is our pole, and in case your poles are rotating, poles may be of like this, and stator would be like a hollow cylinder. So in case you are having stationary pole, this is the case with stationary pole, and this is the case with rotating pole. However, in this case what you have, your armature will be rotating, and you will have armature tooths like this. And similarly here you will have stator slots like this. Right. Now what you can have here, let me just color them for better identification. Like these are the stator tooth or teeth, right? Similarly here now what is in between, that is you are having your conductors here. So it is clear to understand, or very easy to understand, that obviously whatever magnetic reluctance flux will face here, it is not same on the teeth. So if we draw the flux lines, we will see it will be like and similarly here also, means it is only between that stator teeth or rotor teeth and your means machine magnetic structure. So this is known as so how it affects us, like this will create a high frequency ripple. So we can consider it like uh, that these flux at the tooth are stationary with respect to our pole face. Like wherever this pole goes, it carries this kind of flux with them. So now these flux, as they are stationary with respect to pole, so they can produce their independent flux waveform inside our machine housing. What I am trying to say, suppose if you have your, say, let us consider a sinusoidal flux density waveform distribution, and these people are like, oh, whatever, and also here. So what I am trying to say, whatever EMF will induce in your conductor, that is due to this, and also due to this. This variation of means will also cause means generation of some EMF, or means some EMF will be induced due to this pulsation of flux. Now this pulsation of flux, what we can say that if there are q number of slots per pole per phase, then there will be two MQ cycles of tooth frequency for each complete cycle of our fundamental frequency. So tooth frequency or slot frequency you can write like fundamental frequency into number of slots per pair per pole, sorry, per pair of poles. So this can be written as, just a minute. So now we can write the flux linked at a particular instance with n turns of the armature winding at a time t. So this is like psi is equal to this this one is due to main field flux plus the other part, this one
slot
into your cos 2 pi f of t. So this gives us right. So here one thing is clear, that if you take e to the power minus this whole thing, where it goes, again we have reached, okay, that so this is the whole thing here. Now if we take this, let it be our, so flux linkage, if we take, it will be, so this will gives us so this is our expression. Now you can see that the first term, this one is known to us, we are familiar with this. This is due to our fundamental harmonics. Here I have assumed that fundamental flux distribution is we are having a sinusoidal flux distribution. In spite of that, these two triples, you can see that they are producing two high frequency components, and the frequency is considerably high, because Fs, it is fundamental frequency into number of slots per pair of poles. So number of slots per pair of poles is quite often it's a very large number, and you can figure out that it will be how high it could be. So this is very disturbing if you cannot handle this, and it may, these high frequency harmonics in terms of your machine, it won't cause much disturbance, because of its small magnitude, but due to its high frequency range, it can always like produce undesirable effects on nearby communication channel. And nowadays when we are talking about, means most of the things are automated, not only the telephonic communication but for your machine and motor and other power systems operation are also done in remote manner. So it may interact with those signal lines also and cause a significant means unbalancing in your whole network. So that is what means a large oscillation in your network, not by controlling the actual voltage but just by altering the control signal, it can create an undesirable situation. So what we can do to avoid this? As I have said, that we can go for fractional slot winding. What is fractional slot winding? That I have already discussed, like 42 slots and 10 poles. We got it for fractional slots winding. So this fractional slots winding always give a vernier action to balance this kind of flux pulsation. Or other things what we can do, we can just skew the structure. Generally either the stator structure or the pole shoes are skewed to ensure that it is your, like when your armature is located at stator, then we skew the stator structure, and in sometimes when the armature is at rotor, we just skew the pole shoe structure to avoid this kind of flux pulsation. However, I am not going to discuss any more on this because this discussion has got no limit. It is a complete subject itself. So let us wait for your 6th semester course, and let me proceed with some more advanced topic in our related to the present course. Now let us start our discussion about armature reaction. Enough of this design aspect. Now let us study armature reaction. So what is armature reaction that we need to know? Perhaps most of the students already have gained some insight about the armature reaction, and at this moment I am talking about the generator. Now here suppose you have a generator, and then say 3-phase load is connected. Same thing can be done for motor analysis, it can be done for motor also, but let us consider its generator. Actually we will see that it is quite not very important to know that whether you are carrying out this analysis for generator or motor. It is all about the direction of current, in which direction it is flowing, and then you can figure it out all by yourself. So what you are having here, this is a generator. This is our load. Now there is a flow of current through these conductors, and obviously whenever there is a flow of current through the conductor, inside this generator what you can have other either you can have stationary stator structure or stationary field structure. Now for sake of simplicity, let us consider a single phase alternator. So in single phase alternator, what you will have here, say one conductor here that is connected with this line, and another conductor here that is connected with this line, and you are having say a bar magnet is placed, say here inside this slot. A bar magnet is placed, and this bar magnet is rotating. This bar magnet can have projected pole or can be total cylindrical in shape, whatever be the case. Now depending, whenever you load this or you connect some electrical allow some electrical path for this voltage, the voltage that is getting induced across these two conductors. This is the your coil. So whenever you allow them, they will a current will start flow through these conductors, and we need to know that how these currents can means current is how this current will develop its own magnetic field, and how that is means sometimes it may cause problem. So for the starting, we have already discussed our means coil. Now I would like to show you something that is pretty interesting, and I think you will also find it quite interesting. Like, let us, this is our cylindrical shape, sorry, this is a cylinder, and here you are having conductors. Say these conductors are 180 degree pole, means 180 degree phase apart. So if we go for a surface development, what we will find? We will find that here we will have some conductors. Now one thing we can do, like if these conductors are carrying like negative or positive means current at any instance, obviously the conductor that is pole apart will carry, means if this conductor's current is dot, the conductors which are pole apart must have a current that is cross. Now see, okay, first let us, when we go for a surface development that I shown in my first video, how a cylinder can be means we can develop a plain paper from a cylinder, and when we go for surface development we can get a structure like this. So here what I am considering, this is very simple one. I am considering a case where you are having like although concentrated winding, but it may be not concentrated, rather no, sorry, not concentrated, you are having distributed winding, and also it is having some pitch, means the coil is not full pitch coil, it is having some pitch factor. So what is the purpose of introducing all this to you is very simple thing. It is that just a minute. So similarly, after surface development, this is one side, and the other side will also be having this, like first of all, tell me that how many conductors do we have here? Sorry. If you apply your common sense, it is undoubtedly 4 in that one half and 4 in the other half. So the structure will look like these kind of things. I am still discussing a single phase case, not going to any other means 3 phase one, because first let us try to visualize it for what is happening here. So here you can see that if this is the case, then what should be the pole position? like if this is our 0, this is our pi, this is our 2 pi. So like here we are having two poles, sorry, two conductors carrying dot current. Here we are having two conductors carrying cross currents, and similarly here you are having two conductors carrying cross currents, and here two conductors carrying dot current. So basically how the coils are connected, like here this is one set of coil, right, and then it forms a total thing. You are having only one for one phase we are considering. Now one thing is very interesting to note, that this is a short pitch, like this is a corded distributed winding. So if this is a corded distributed winding, and when there is a flow of current, so when we discuss it for DC machine, what we have discussed a triangle kind of shape, and our means at that time we considered full pitch distributed slot. When if you are not able to recollect it at this moment, you may please go to that DC machine armature reaction video, where you people ran a trend of hitting dislike button. You can go there, that DC machine armature reaction video. In that video you will find that how, while we are talking about armature reaction, we are considering that the armature conductors, the placement is a full pitch distribution, and there is like infinite number of conductors, like there are very close to each other, right? Like here we can see that along our machine periphery, I do not know how whether you can recognize this one, because here only black color is available. Let me just try to make it visible for you. This is the periphery of the machine. Now if it is stationary armature, then it is the inner surface of the hollow cylinder, and if your armature is rotating, then it will be the outer surface of the solid cylinder. So whatever be the case, now you can see that this line is here. It is the line after surface development. Now the question comes that what kind of MMF we can expect for this armature reaction. Previously it was triangle for DC case, because in that case it was easy to claim it is triangle. But if you now consider the amount of okay, let me be more particular with the definition. Here this is the amount rho, that is the amount of pitch. This angle is also rho. Fine. Now consider that how much amount you are having here in this span. This is so if that is the case, then obviously it is like Okay, don't get confused that this pitch is like your this P. Just let me remind you something. Like here, we have started this diagram earlier. Sorry, we have started this diagram earlier. Now try to understand one particular difference. Like when you are placing these conductors, it's okay. Like here you can see that pi x plus rho here, yes, pi plus x pi is equal to pi, sorry, rho plus x pi is equal to pi, where rho is the amount of cording. So if you want to follow this analogy, this can also be viewed like here it is x pi plus rho, or in other way we can say that it is x pi plus rho by 2 plus rho by 2. Like when we will bring this whole thing in the middle of these two poles, then what we will see here, it will be rho by 2 amount of means rho by 2 will not be covered by any conductors, and here also rho by 2 will get. So same thing I am trying to tell you, that if you want to follow this definition, then it will become rho by 2. I am making it rho by 2, otherwise you will get confused. So it will become again pi minus rho, or whatever it is, or x pi. However, unlike means uniformly distributed winding, in uniformly distributed winding we have a privilege. Like what we will get, we can always say that for uniformly distributed winding, suppose had we considered another few coils here, so you can see that till you reach the center line of this conductor, they will carry current in one direction, and after the center line they will carry current in a different direction. So you will get MMF distribution quite similar to that for our DC machine, that is a triangular MMF, like this. But here, fortunately, unfortunately, we do not have that much conductor. Well, so that many conductors present. So now here we must have to determine that what could represent our this shape of this MMF waveform. So applying our common sense, instead of involving too many technical terms, we can see that these two, whenever you are moving for these two, they will give rise to your MMF. So, but however, after this, there are no further conductors. If you move towards the center line of this conductors group, there will be no further conductors you are encircling, or that magnetic path is encircling. So if you move in this direction till you get these conductors that are carrying current in opposite direction, you will have a steady MMF value, that is capital A. And once you reach here, when you will sense a different MMF or opposite MMF produced by these two conductors, it will become this. And since it has to be a half wave symmetrical, so you can expect the similar kind of things for this side also. So this is also A. Now here what we can write, that if we try to figure out the components like for rth harmonics, then like this flux density this MMF, and also we can say that MMF is proportional to flux as well as the flux density, right? Like if we consider, first of all, here we are considering a linear analysis, we are not considering saturation or anything in our account. So here now if this is the case, then or even if for this non-sinusoidal MMF also, we can carry out the Fourier analysis to find out their waveform. Now see, as I have drawn the way in a neat manner, that it seems it is having odd symmetry as well as half wave symmetry. So odd symmetry and half wave symmetry together means keeping in view these two trait or characteristics of this armature reaction MMF, we can claim that the whatever we will get will be having only odd symmetry harmonics, or meaning only sinusoidal sine components will present, no cos components will be there. In addition, there will be a case of your half wave symmetry. So only odd order harmonics will present. Typically, if you try to write it at any time point, your or for any space angle, you can write that it is what is your alpha? Alpha is when you will move in this direction, that is alpha. So A alpha for any particular value is like this. Now what you can figure out that this is, from this you can figure out the value of rth order harmonics. That rth order harmonics you can figure out the will be uh, 4 pi. Then we need to carry out two integration. One is for where the MMF is varying from 0 to A, and another part where the MMF is means varying from our, or means varying in a constant manner. So, and here we are considering it is having a quarter wave symmetry also. So we will consider till pi by 2 only. So there are three segments. One we can draw where MMF is 0, another segment where it is varying linearly, another segment where it is constant. So that is why I have written 4 by pi here. Now the first part will be how from where to where it should be. Now let us see, let us consider that this is having a span of beta, this where you have placed two conductors, or we have placed two conductors, they occupy beta angle amount means within this total span of 360 degrees. Similarly, if they occupy beta, here also it will occupy beta, this will occupy beta 2, and this also. Now, so if this is beta, what we can write like rho by 2 plus beta plus rho by 2, and that will be here. Now, since we have developed it in a linear fashion, surface development, so what would be the slope of this rising line? This slope will be a by beta, so it is a by beta, then how long it will continue, or means what should be the factor? It is like alpha, that is the dummy variable, minus rho by 2. Basically this gives you, what happened to this? What? In this region, when you are within rho to beta plus, rho by 2 to beta plus rho by 2, in this region at any point it is like just having a linear line with slope m. So at any point, how to figure it out? Say if this is our x1, then y can be written as m into x1. So what is your m? M is here, that is a by beta. And what is your x1? x1 is the distance, alpha, that is the space angle at any time. Suppose you are here, that is your alpha. Alpha minus rho by 2 will give you the x1. Well, so if we follow this logic, the alpha minus rho by 2, then sine r alpha d alpha. Obviously there is no point of considering cosine because they are not present, and the second part will be where the mmf was constant pi by 2 to beta to pi by 2. Here it is constant a, so a sine r alpha d alpha. So if you do this, then what you will get? Obviously, keep it in your mind that I am nowhere doing it for our original field. Original field may be sinusoidal in nature or sinusoidal in shape, but that sinusoidal or maybe non-sinusoidal in variation with respect to speed, space angle. But what I am doing right now, I have forgotten everything. There is nothing, only thing present here is the armature reaction. So we are doing everything as if the field flux or other things are not present. We are assuming linear analysis for for our sake of simplicity, or for having reducing the computational burden. We have considered this. Now see what we will be getting, like this will later result you, if you evaluate that, you should get 8 by pi a beta r square sine r beta by 2 cos r epsilon plus beta by 2. Well, so this is one typical case where it is distributed but do not cover the total area. And now, so for one such MMF distribution, and we have explained that how can we get such kind of MMF distribution, and we found the MMF shape also correlate well with our understanding. Like when there is conductor, there is a rise of mmf or fall in mmf, but when there is no conductor, in the no conductor zone, it is continuing with the value of mmf it already have in that previous zone. So now here you can think like we'll study a few special case. What are those special case? Let me show you. The special cases are if you have only one winding, right? What I am trying to say this is alpha. You are having only one winding here and another winding here, another winding here and another winding here. So this is pi 0, this side is 2 pi, this is rho by 2, now what type of mmf distribution you can expect? Since we are having only one conductor, there is no such scope of steady rise. It will be just like step. So you will get that means beta part is now 0. Whatever you have, you are having it like this. So what about AR? AR how to find? See, you have to apply the limit like 8 pi A by R beta R in here it is sine R beta by 2 into cos R cos R P by 2 plus beta by 2. Sorry. Just let me check whether it is going. Sorry, here it is actually rho by 2. Right. I forgot. Actually, I am looking for my old notes and there it was written in eta. So it's not epsilon or eta, it is rho. So it's correct now. So yeah, otherwise I think I have not made any mistake. So it is rho by 2 plus beta by 2, and then what you need to do, you have to apply a limit here. What is that limit? So you can see that this part will give us 1, like limit x tends to 0, sin x by x gives us 1. So what will have remaining, that will be 4a pi r cos rho by 2. Sorry, r rho by 2. Now when you will make this rho by 2 0, like
rho by 2 is equal to 0 means what you will have sorry 4a pi r cos 0, that is 4a by pi r. So how to calculate a? A is very simple, that n into I, whatever be the value we will get, that is the value of a. So this is two distribution. Another thing we can have is like this we called trapezoidal distribution of flux. What would happen that if we make rho by 2 0, what I am trying to say, so what would happen if you have this rho by 2 is equal to 0, like so you are having only beta but no rho. So how from that expression it is like AR is equal to 8 by pi A beta r square sine r beta by 2 cos r rho by 2 plus beta by 2. So what you will get here, this will simply give you 4 by a pi beta r square sine r beta. Well, now we'll study another type of distribution. Now we will see what is most common in our DC machine, that is triangular full pitch distribution. So if this is A, this is also quarter wave symmetry, having quarter wave symmetry, so we can figure it out that how to, so basically we have to start it from this equation, like and then what we need to do, that if this is uniformly distributed means you are not able to figure out the very uniform distribution means the case where Q, the number of slots per pole per phase, is very large, almost infinite. So it is very difficult for you to figure out the slot
angle between two adjacent slots. Although when you consider the group will span certain span, but not the individual slots. So if beta is equal to pi by 2, then what you will see that for such case you will have something like right, and because beta is equal to pi by 2, if you put, then you will get this one, and depending on the r you will have different value of sign. Sometimes it will give plus value, sometimes it will give minus 1. So it is in this way, minus 1, r minus 1 to the power 2 we have written. And what if we have triangular distribution with trapezoidal pitch? So in case of triangular distribution with fractional pitch, that can also be found, like what I am trying to say, it is like it is rho by 2, this is pi by 2, this is pi, this is 2 pi. So basically here you do not get any constant mm equilibrium, everything is varying. So it is like rho by 2 plus beta is equal to pi by 2. So let us again consider that expression, that is AR is equal to 8 by pi, 4 pi. This equation will be rho by 2 plus, here it will be pi by 2, then A by pi by 2 minus rho by 2, because beta is pi by 2 minus rho by 2, then alpha minus rho by 2, then sin r alpha d alpha. So if you evaluate, you will get something like 8 by pi A, this one will give you this, like let it make it beta to represent it in a compact form. Beta r square into sin r cos r pi by 4 plus rho by 4. Okay, so this is the case. Now we will go to the most generalized distribution. What is that? This one you will also get in any common book like Slangs or any other book. So here we are having distributed slots, but slots are distinguishable, like you can calculate the interslot angle. So this is the case. Now obviously what we can see that the peak EMF value, we can figure out the peak EMF value if we have, let us consider that we are having number of slots, that is 2n per pole, and n is the pair of slots per coil group. Like this you can consider it as like Q also. Then the total number of like the peak EMF will be how much? That will be 2qzi by 2, where the small I is the instantaneous value of the current and z is the number of conductors per slot. Each of which is carrying a current I. So it becomes QZI, right? So if it is QZI, we can write it like this one is equal to NPI, where NP is the total number of your turns per pole. Well, so if this is our case, then now try to understand that what kind of harmonic MMF will get from this structure. Think about it. First, note down all these details and then think about it. So, what we'll get here, like if this is our NPI, so it is NPI. Now, the harmonic MMF AR, this we can visualize like when we had two coils in that way. Like every move you are making, say, let me show you the current direction also. Say these are having dot and the other end who is having cross. Now it would be like quite similar to the first discussion, the trapezoidal one. The only difference is that if you recall, at that time we considered that two conductors, they are very close to each other, very tightly placed, and therefore it was beta. However, here what we can see that there exists a small angle between these two slots, namely gamma, between each slots. So when you means cover one slot, what you will get if you consider the MMF formation, it will be like this until it sense the presence of the second slot, then it will be this. So basically you will have a staircase like formation that will continue till it sends the current carrying conductor of opposite side. So similarly you can get another one here. So this is the case. Now this is the maximum magnitude A, right, and the amount of chording is rho by 2. So here what we can write when we'll try to write it for this, we will take the help of that distribution, rectangular distribution, like we will take the help of this one, right, with different value of rho by 2, we will take the help of this one. So how can we write it? It will be as the first lot, it is it will be the second one will be for second slot. What is your means? If you consider only this slot is present, only these two pairs are present, then they are for this pair the amount of cording is gamma from both sides. Then for the next one it will be how much? 2 gamma, and at the end it will be we have reached the end of the page also. So however, at the end it will be r rho by 2 plus n minus 1 gamma into, sorry, n not n, q minus 1 gamma. So q minus 1 gamma into okay. So this can further be simplified as like AR is equal to 4 by pi A NR one by sine. So this will give sine, here it will be r gamma by 2 into this one sine whatever remains like cos r rho by 2 plus gamma plus cos r rho by 2 plus 2 gamma, and the end plus cos r rho by 2 plus q minus 1 gamma right. So if this is the case, then this one further can be simplified like this way. I am taking this 2 to adjust another 2 in the numerator, and after adjusting what he will get it's like rho by 2 minus gamma by 2. This form, sorry, not here. Rho by 2 plus, here it will be how much? It will be 3 gamma by 2 minus sin r rho by 2 minus 3 gamma by 2 and so on. You at the end will get, there will be terms, at the end we will get sin r rho by 2 plus your that one, sorry, yeah, sin r rho by 2 plus q minus 1 by 2 alpha. Sorry, gamma. So you can see here that these things, if you simplify, I had the derivation, you just cannot figure it out where I left it from, unfortunately. So what we will see that this whole thing will boil down to an expression that will be like by 2 sin r just a minute. Yeah. Sorry. Now I have corrected it. So here the last term will be quite complicated. So what we can see, now I recollect it, that all these terms will cancel out each other, leaving us with this and this. So we are going to write them. They will give us what? Yes, now I recollect. They will give us sin r rho by 2 plus q minus 1 gamma by 2 minus sin r rho by 2 plus, sorry, minus gamma by 2. So if you further modify them, you will see a very strange fact will be getting, that is 4 pi a n r square 1 by 2 sin r, sorry, this one gamma, r gamma by 2 will be here in the bracket it will be like sin r I have also made a mistake here. Actually in that I wrote everything in terms of n, and in our discussion this time I have assumed it q. So please change it. Just let me check whether I have written it correctly or not. Yeah, the trouble starts here. It is QR. So yeah, now it's okay. It is like 4 pi a by q r square 2 sin r. This here it will have you sin r q gamma by 2 into there is another, yes, here it is not r square, it is r, so it is r, so sin r q gamma by 2 into cos of r rho by 2 plus q minus 1 by 2 gamma. So this whole thing, what we can find out, we can write them like 4 pi a by q r. Now this whole thing is like we'll get 1 2 here, like sin I am applying the formula sin a minus sin b, so it will give us 2 sin a plus b by 2 into cos a minus b by yeah, this one. So this way what we will get, that it will be you will get this formula. Now see, if that is the case, like the formula what I am trying to talking about, not sin a plus b, rather sin a plus b minus sin a minus c. So if we do it, we will get this one. Now what is the things here we are getting, or yeah, so what we are getting, like 4 pi a q r is you can see that this one, these two will cancel out, so these will become that with this it will give us the expression of or breadth factor, and the second term will give us an expression of your pitch factor, right? So it is interesting to note that how the distribution factor KBR, in our case, what is its value? Its value is we are getting sine R Q gamma by 2 with R Q sine R gamma by 2, and how it is like you are having KPR is equal to, we are having cos rho by 2 plus Q minus 1 by 2 gamma. So this whole thing, we can write it like R is there, so the whole thing can be written as what is the value of this Q minus 1 by 2 gamma? Do we expect? Can't we write it like it is cos R gamma by 2? Think about it. What is the angle shift offered by this Q minus 1 by 2 gamma? So this can we write it? Do remember that cos is positive in your first and third quadrant. So if you have q number of conductors, so q minus 1 gamma by 2, they basically give you the remaining set. So it is cos r rho by 2 you are getting. Now another few things we need to mention here, like if we know the peak value of current, that is I peak, then it is how much? Say if our I we are basically actually talking about ARM, it is the maximum value, that will be how much? 4 by pi 8p I peak into KBR KQR will be 4 in P. I peak will be root 2 into IRMS by pi KBR KPR. So that will give us here one R term will be there, 1 point R NP IRMS by R KBR KPR. So I is RMS is the RMS value of conductor in each slot, right? Now we'll see how we can figure out this is the total amount of armature MMF produced by it, how some of its part will represent the demagnetizing MMF and some of it will represent the cross magnetizing MMF, and for what type of current is responsible for production of what type of flux that will let us study. So now we have understood the means armature reaction produced by one coil or a set of coil. However, we must extend our this expression and study to understand that how armature reaction actually takes place in reality. So for that, let me draw something like let us forget for the time being that who is rotating and who is fixed. Let us consider it is the motion of the relative motion that is responsible for our EMF production. So let us consider this is the two ends of one coil. So if this indicate the direction of motion, like the conductors are moving in this way or the fields are moving in this way, anyway it is the motion is constant. So what type of you will get, it is easy to find out, like S you have to apply your this is S, this is motion, so find out the direction of induced EMF using right hand rule. So what right hand rule states, like you will be able to see that it is indicating your like this will be a dot, means the conductors will be such that EMF will be induced in such a manner, and here this will be cross. Now this dot and cross doesn't make any sense until unless you connect a load. Now in AC we know that we can have three different types load with unity power factor, load with negative power factor, load with positive power factor. So if this is the case, then it is like that obviously EMF, what about EMF induced? EMF, as we discussed, for the time being let us consider that we are having pure sinusoidal flux distribution and the flux density curve only contains fundamental harmonics. Then your EMF will also be sinusoidal in nature, and that sinusoidal EMF will also result in, like you will have curve like this. consider, obviously this curve is drawn with respect to time, but here one interesting things to note that who determines your, means what is the angle difference between these two. Electrically it is always pi, and what is your frequency, that is your omega t, where your omega is in radian per second, and this omega t is equal to, so as we have means mentioned 1000 times, like this omega t, the mechanical rotation omega, that actually governs the frequency of induced EMF. Now if that governs the frequency of induced EMF, you will get an induced EMF like this. If we consider there is only fundamental flux is present, no flux is sinusoidal in nature, so this will be the nature of EMF. And undoubtedly this peak you will get when this means peak will be get when the flux density is at peak value and when the flux density is at zero value. Then this will also give you 0. Now interestingly, that in case of AC, unlike DC, your, and that's why I also asked that what is the power factor experienced by your DC armature circuit. You people didn't answer, but if you try to answer and investigate, then you will understand another striking things, that in case of AC machine, this is the alternating EMF, and we have the flexibility that we can connect any load and they will draw current according to their not only their impedance value but also according to their power factor. The current drawn by the load will maintain certain angle with our this induced voltage. So obviously this current, like let me draw one more thing, like this is our induced voltage. Now let current is having a angle of lag psi. Now this current, this blue color current, can be expressed like two components. What are the two components? Let me draw it like one is that is in phase with our current, and the another one that is in quadrature with our current. Just so this one was in phase component of current, and here you will have another component that is 180 degree, sorry, 90 degree out of phase. So how you can draw it, it will be like sorry. So clearly, if you consider the this yellow color line that is in phase with your voltage, and if you consider the red color line that is in quadrature with your voltage, and if you do point to point addition, actually my drawing is not correct, but if you do point to point addition, you should get the resultant current that is shown by the blue curve. Okay. Now, why I have drawn all this and means consume some of your time, because to make you understand one very simple thing, that is we can draw now. The in phase current was drawn by yellow line, so that in phase current will reach their maximum value when you are having your means EMF reach its maximum value, in phase current will also reach its maximum value. So we can write here, these are the points where the coil is having maximum EMF, and here it is maximum in phase current. Now whenever it is a maximum in phase current, you can see that what is the flux produced by this in phase component of current. You can consider that they are producing flux in this way, like so. It is easy to understand that if you draw this current, you will see that they are having their maximum value here, right? Like trapezoidal shape you will get, or if you have more conductors here, then you will get angular shape, but it's trapezoidal shape you will get, and therefore it is easy to understand that at interpolar region this one offers maximum like magnetizing due to this current. This is in phase component of current. Now similarly, what do you have? Now what is the magnitude of and this producing like this is producing your cross magnetizing action, because the EM means current is generating flux in that interpolar region, that is cross magnetizing flux. Now what about your like the other one that was red? Now try to understand that red one is very interesting. For now, as we have separated the now when here I have drawn a current carrying conductors that is lagging, means how to draw the lagging and leading also I have drawn. How to draw it? First of all, try to understand. Suppose you have a cycle, means you are holding a cycle tire or cycle tire tube by your two hands, right? And it is this tire tube itself is moving in counterclockwise direction. Sorry, clockwise direction. Now, if that is the case, then any point on that tire tube, say one point here, or let us call any band on that tire tube here, and another band here, obviously this one will come first and this red one will come after certain time, and that angle subtended by the center of these two will be let us it be 90 degree. Now when you go for surface development, what you can do, you just cut this one, right? You just cut your cycle tire tube and then flat it or stretch it just like a straight line, just like a rod. Then what you will see that this part, that is that you will get after a further 90 degree rotation is representing the lagging current. The issue of representing it that, like, since the lagging current maximum magnitude, any current carrying conductor that is carrying 90 degree lagging current will reach its maximum magnitude after the in-phase component of current reach its maximum magnitude, means after 90 degree the in-phase current reach its maximum magnitude, the lagging current reach its maximum magnitude after 90 degree of in-phase current. So here it is the beauty of this system that our time phase angle and space angle are same. So means electrical space angle, obviously don't get confused with the mechanical space angle. Mechanical space angle can be anything, but electrical space angle is always 90 degree between these two. So we can represent this, there is only one coil, that is say this coil, but it is carrying two components. One is leading, one is in phase component, another one is lagging current component, and we can consider that this lagging current can be represented by this red line, while this lagging current is carrying actually the in phase component, means the either you can see the total current is flowing through this coil, or you can break this current in two components. One is in phase, another one is lagging, and in phase current will exactly follow the phase in of induced EMF. So in phase current will be in time phase with your induced EMF, as well as it will follow the space angle variation of induced EMF. Like as our electrical space angle and time phase angle are same or identical, so we can represent the variation with respect to any of them, like either electrical time phase angle or electrical space angle variation. So whatever variation will be followed by our induced EMF, the in phase component of current will also follow the same pattern. However, the lagging current, since it will reach 90 degree in electrical time phase after the in phase component reach its maximum magnitude, this same current can be visualized that instead of having a single coil that is carrying both the in phase component and the lagging current component, we can visualize it as if we are having two coils. One is 90 degree, the two coil center lines are 90 degree apart from each other, and both of them are carrying in phase current component. Both of them are carrying in phase current component, however, or unity power factor current component. However, the one
that is already lagging behind, means in space it is lagging 90 degree, obviously it will reach its magnitude 90 degree. So this coil which I have represented here, it is a virtual one, it is not the actual coil. Similarly for leading you can draw it. So in a nutshell, after drawing them, what you can see that as this can be represented, this lagging current carrying coil can be represented as a means current carrying coil shifted in the direction of rotation by an angle 90 degree. Now for this kind of current flow, we just analyze what type of flux will be produced by this coil, and we already know even if you shift, then the flux production for this pattern of current won't alter. As long as you are maintaining this pattern, you are going to get similar flux pattern produced by this current carrying conductor. So what we can see, it is very interesting to note that this, see, this is in opposition. Your south pole, it is acting as a sink, so it is trying to draw the flux line towards it. However, this coil is producing flux lines or EMF in opposition to your main field flux, and therefore what you are getting here, obviously if you draw this side, actually this is what, this is current carrying conductor. There are two sides of the conductor, means if you expand it, you will get, this is basically saying like, if this is 0, this is pi, then again we will have pi to 2 pi, and in that region they will produce a current, sorry, an MMF in this direction, that is in direct opposition with your north pole MMF. So basic things what I am trying to say here is very clear, that here your MMF is in direct opposition with your main field. So that is why we can say pure lagging current is purely demagnetizing in nature, and similarly the leading current has an effect of strengthening the main field flux. So these two are very important example, and we can draw an important conclusion that generally what we have either we can have 2-3 extreme cases are possible, either purely resistive or unity power factor load, purely inductive or 90 degree lagging load, and purely capacitive, that is 90 degree leading load. However, generally we have all our load can be expressed as a combination of these three. Like if you have a load with good power factor, then obviously the resistive power or resistive load component will dominate, and the inductive current will be comparatively small. If you have something with slightly leading power factor, then instead of you have inductive reactance, you have to consider there is a capacitive reactance is present, and you will get corresponding boost. And here it is very interesting to note that we are considering the generator case, and this is not surprising. Like when we study in transformer also, we saw that for capacitor capacitive load, what we have, capacitive load causes negative negative regulation. So how negative regulation takes place? Definitely capacitive reactance, the current was flown in such a way that it strengthens the main field flux. So similarly here also you are getting the same thing, that your generator output terminals can be considered as the transformer secondary terminals, and whenever you are connecting leading load, that is basically trying to cause negative regulation of your generator voltage. However, because it has an inherent effect of strengthening your magnetic field, and if someone strengthen the magnetic field flux, obviously from that expression E is equal to 4.445 F
that one, you can figure out that phi will be more for if you consider linear assumption. We are here, we are not considering the saturation or other factors come into play. So obviously someone can strengthen your field or you will get a very good negative regulation. So these are there. Now let us do one thing. Now, even if these things are not very clear to you, let us try to explain it in the light of, or let us extend our understanding of DC machine armature reaction here. I hope that for that video you have means run a trend of hitting dislike button. There were so many dislikes. So I hope not only hitting dislike button, you have also means seen or means have watched the components or means what is there, sorry, content of that video. So if you recall that one, then you will see that for coil, when we have coils like this, let us consider this is the direction of motion. First of all, in case of DC, what we have generally this armature periphery, rotating armature is filled, means totally congested with conductors, and these conductors are placed so dense that adjacent slot angle means or intermediate slot angle becomes almost zero, and you get almost a smooth triangular distribution, not a stepped one. So this is the case for DC, right? We have drawn it for DC. If you watch the video, you'll see that this is the case for armature reaction. Now this armature reaction has also means we can see that where the armature reaction is maximum and where it is minimum. Now what is the problem with this structure? Not problem, rather what is dissimilar or not even dissimilar, what we are trying to do here or interested to do here, it's very simple thing. Let us consider only a single coil that is under the direct influence of pole. So where you can get direct influence of pole, obviously when you place or your coil plane coincide with your field axis, then you will get maximum EMF induced in them. So that is the case where you are having maximum EMF induced in them. Now, here this coil will get maximum EMF. Now from this position, what we can see that the in phase, let me draw the surface means development. Here you can see that space, this is that space, if we develop the surface, this is known as surface development, means cutting conductor, and then you can see that this can be represented in this way. This is the coil position and this is giving us maximum EMF. Obviously the conductor, that is coil, that is carrying maximum EMF, we are considering a load that is connected with this is having a current or carrying a current like the load is carrying a current the in-phase component we represent it using IRET, and the lagging or leading current by IXCP. So this as I have mentioned that any current, suppose this I is like Im sin omega t minus theta. So this can be represented as one component that is having REM sine omega t, and the another one is like I plus minus I REXEM cos omega t. And when you consider these two, this IXM cos omega t can be figured out, or means can be represented by a coil that is having an induced EMF E cos omega t induced across them, and the coil is connected with a purely resistive conductor. So what I am trying to say is that in this DC machine, here you can see that the in phase component of current, if you consider they are draw the field lines, and what about these lines? This is like so it is clear that if we draw its resultant, it is in quadrature with these lines of force. However, what we can see that for this is due to this IRM RE sine omega t, and accordingly you can means here I have drawn the current also. So you can see that there we are having two current. One is in phase current drawn by this waveform. This is also interesting to note that at first we are getting negative waveform, but it is means that is from where we started our observation. So there is nothing wrong in this. So what you can see here, or what I am trying to say, that is basically very clear. So here you can see that I have drawn this waveform, and now as I said that this can be represented by a combination of coil that is exactly lagging behind this. So how to draw the lagging coil? So if we have to draw the lagging one, as I have shown this lagging by the saffron color, let me draw this with the saffron color. Like your coil for lagging, what you can expect that this dot for lagging will be 90 degree in clockwise direction, and this cross for lagging will be 90 degree in clockwise direction. So this is the position of the lagging coils. Now applying your that right hand thumb rule, you can figure out the direction of magnetic field produced by them. You see that this coil, as it is carrying current into the plane of this this board or whatever, then this will produce a current that is or MMF, that is and similarly this one is also producing so basically you can draw for this, it is means behaving like you have placed a bar magnet whose south pole is in phase under your original north pole, and whose south pole south face is under whose north face is under your south pole. Means what I am trying to say that is as if you are having a bar magnet like this. Fine. So I hope you get some of the idea of this representation, that how we can represent them. in reality. But do remember that actually these bottom green coils only exist in reality. They are carrying the current having some phase angle. So that current we are considering that actually there is not bottom green also. There is originally it is a white color one, that means the main coil, and obviously it will carry current. Now this main coil we can means break this main coil or main coil current like it is produced by, obviously this main coil current will produce some like some flux or some MMF. So in order to study this effect and in order to exploit the orthogonality between the cross magnetizing and demagnetizing component, what we can do is that it is very simple. Yeah, we can draw the in phase component. This is also virtual because no current, no physically coil is carrying just the resistive component or just the means. Similarly, no physical current carrying coil is there in quadrature that is carrying a current in phase with your induced voltage. Yes, I didn't make any mistake. It is, I am consciously making this statement that when you are drawing the saffron colored coil in that particular position, that is exactly in quadrature with your main field, then they should carry a in phase component of current, and that in phase component of current will act as if your main coil, these two are carrying a purely lagging current. So this all, now let us try to, now this is the expression I have written like this. Now one thing that was for generator. Now we will try to do it for motor also. Remember that in that case of DC I told you, it is in case of DC the nature of the field flux, sorry, nature of the armature flux that tries to means like tries to increase the magnetic flux density near the your trailing pole tip, right? In near the trailing pole tip, and so it is in case of generator, it is the means like you can figure out that MNA is exhibiting a tendency to move towards the direction of rotation of the generator with your means if you put more load on your generator, more if you connect more electrical load with your generator, then there is a tendency of MNA to shift in the direction of rotation, and in case of motor it is in the opposite direction. Do remember that for motor and generator, now we are considering the same case here for starting armature reaction in our AC motor. Now how AC motor current can have different power factor, that we will discuss later. Now here this AC motor power factor, obviously it is this span. Now this one, like this AC motor power factor will be like yeah. So do remember one thing, that in case of AC motor, actually it is not the direction of rotation is not generated by the prime mover, rather it is the torque generated by your interaction of flux and current, and in this case the torque direction can be found using left hand
Fleming's left hand rule. So if you try to follow Fleming's left hand rule, however, here you have to do a little reverse engineering, like you know the direction, in which direction you need to rotate the motor, you know the flux line. So now you can figure out that in which direction you are having your middle finger pointed. So that the middle finger now under south pole, you can see that now the current is coming out of the plane, and under north pole the current is penetrating into the plane. So here it is very clear that it is just the opposite of what we got in case of generator, when for same direction of rotation induce different direction EMF, and that is quite obvious because for motor you have to reverse the current direction if you are trying to move it in the same direction. So now for this is actually then obviously the in phase current will, like the previous case of generator, will be in phase with the coil, or in other way we can say that the in phase component of current can be represented by a virtual coil that is totally coplanar with your main coil and carrying a reduced amount of current that is particularly in phase with your main current, or not main current, rather main EMF. And what about the leading current? In case of leading and lagging, see, the leading and lagging will get the similar way, leading and lagging. This is leading. Now see that there is a problem. This is for generator. For leading current, you can see that just a minute. That one was for generator. I got I have to notice that. This is for motor. So the leading current is exactly, we are doing the same thing to get the leading current. Leading current should be 90 degree ahead of the main or in phase component current coil. So basically, how to get the leading current coil position? Just by executing a motion in the opposite of your direction of rotation. So here we are considering the direction of rotation takes place in clockwise direction. That is why we are considering the leading current is leading current coils should be shifted in anti-clockwise direction. Had we considered that the torque is in, or the motor rotation is in counterclockwise direction, then leading current coil position could be found out by shifting it 90 degree in clockwise direction. Do remember one thing, that leading current coil always moves is always 90 degree apart from your main coil, and the shift, the direction of shift depends on your direction of motor or generator rotation. In case it always shift in the opposite direction of your generator or motor rotation. So this is the direction of leading current. Now unlike the generator case, see here the beauty, the cross magnetizing current or in phase component of current, they are again producing the similar kind of effect that they did for generator. But in case of motor, here we can see that the leading current is opposing the main field flux. The leading current is opposing the main field flux. So that is very problematic for us, because not problematic, like
what we can consider that when motor will start consuming leading current, there is a chance that what would happen to the torque? The torque may increase or decrease. What? If you keep current constant, current magnitude constant, and change in power factor to leading, obviously your torque produced by the motor will decrease. Why? Because your resultant, do remember one thing, these current carrying conductors always experience resultant flux. So when your motor is carrying leading current, it produces a demagnetizing effect on the main field, and that main field, due to demagnetizing, it is actually weaken the resultant flux present in your system, and in a way it will produce less amount of torque. It will not be able to give you a considerable amount of torque. And on the contrary, the lagging current, that is now they are producing the magnetizing action. So in a nutshell, let me tell you, for generator, lagging current demagnetizing, leading current magnetizing. For motor, lagging current demagnetizing, magnetizing, leading current demagnetizing. For generator, drawing a lagging current will give you negative, means positive regulation, and there is a high chance for generator, if they draw leading current, if they supply leading current, there will be like negative regulation. For motor, if they draw lagging current, the motor will produce a very good, means high torque, because this will means lagging current is going to strengthen your main flux, right, main field flux. So now for same magnitude of current, if they are flowing through your coil, they are under the action of a flux that is greater than the previous case, or the motor case when its coil is drawing unity power factor current. And if the motor starts absorbing leading current, then obviously it will try to demagnetize. And see another beauty, that absorbing leading current means what? Absorbing, if means someone is absorbing leading current, it is like if I borrow 10 rupee from you, actually you are borrowing minus 10 rupee from me. So similar logic, that if someone is absorbing, motor is always current is absorbing. So if motor is absorbing leading current, that means actually it is giving the lagging current. So there is no contrary, that in case of generator also the lagging current motion was outward, and in case of motor, as the current is flowing inward, that is why we are saying leading. But if we consider for the motor that same current, then we can say that it is not absorbing leading current, it is delivering lagging current. So that is very beautiful thing. You can hate me, you can hit dislike, but you can't hate this one, this beautiful phenomenon, that when someone is absorbing leading current, it is delivering lagging current. When someone is delivering leading current, it is absorbing lagging current. So similarly, when the motor is absorbing lagging current, basically it delivers leading current. And accordingly, we are getting same action. What was there for generator? That when the generator delivers lagging current, we got demagnetizing action. And here, if when the motor absorbs leading current, we are getting the same demagnetizing action. So that is the beauty. Anyway, now instead of becoming emotional with the beauty of this entire system, let us try to develop some analytical form that will be handy, and we can, like here I am just doing this analysis. If you have noticed, this entire analysis I have done for only a concentrated coil, uh, probably singleton concentrated coil. There is no distributed winding, nothing. So a singleton coil gives us so many things to it is so thought-provoking, so brainstorming. Now we will try to extend this to a case of multiphase machine with multiple conductors distributed over the space as well as corded or whatever may be. Winding is already engineered to cater some other need, some EMF equation. One thing that we are really fortunate that if you do some manipulation to means take care of your EMF wave shape, like if you distribute your winding or if you means make your winding a short pitch one, then the similar effect can be realized for armature means armature MMF also. So that is a very means means it's a great blessing on us because for if you once calculate the distribution factor and pitch factor for certain harmonics, then that distribution factor and pitch factor remains applicable to calculation of MMF produced by the same coil when that coil is drawing some current. Well, so let us try to see what we can get. In order to analyze, let me draw the diagram. Why I am trying to draw the diagram in front of you, not to make you bore or puzzled, anything, just to show you step by step so that you can follow it and you can use this one for your means. If I have a means notion that if I draw it in front of you, then you could understand it quite well. Obviously, I am not means my drawing is very pathetic, but I will try my best to make sure that whatever I draw that makes sense. Now here, this is our north pole, this is our south pole. Here we are considering rotating armature, but you can get identical effect for means rotating armature means you are having a solid cylinder and armature conductors are grouped on them surface or lateral area of that solid cylinder, and for others you will have for that other cylinder is for your stationary armature. You are having a hollow cylinder whose inner lateral surface are used to place your conductors, and inside that you are having poles embarked on a solid cylinder that can rotate freely inside your machine. Now see here, let us
draw the axis. Now let us draw a coil. Now this coil here, this is your coil plane. This coil plane is making an angle theta with this. So you can see that any time point for any instantaneous angle E theta can be written as E omega t is equal to Em sin omega t. Here we are considering the generator case. The same thing you can do it for motor also. Now let us draw another line, that is a line connecting the north and south pole and passing through the center of this center line of this cylinder. So passing through the Now think about a coil. Now what is your coil plane? To be very precious, to be very precise, let me draw the coil first. Just a minute. Let us draw the coil side. Well, so what I am trying to say that this is your means cylindrical armature, right? Here this coil, this is one coil side, and in the other side you can see that this is one coil side, right? This is one coil side, this is another coil side. So now you can see that this is the view which we are getting, right? This is actually the front view. If you hold a cylinder like this, then whatever you are getting, you will get only here the dot and here the cross, right? Now see, these are the line that I have drawn on this curved surface is representing the line of your conductors, right? And here you can see that if this is the line, like the conductors are carrying current in this way, so what we are getting here, it's very easy to understand that conductors is like conductor plane is like a plane. This is the plane. Suppose a rectangle is placed here, a rectangle plane is placed here. That edge of the rectangles are the two end of the conductors, right?
So why I am showing you all this, because as I am discussing the surface development, you might have a wrong notion that uh, the plane on which I am talking about, that MMF vector is perpendicular to a plane that is after surface development. No, it is the plane that is as if you are placing this kind of rectangle, yes, rectangular plane inside this cylinder. Your cylinder, it's the armature, and this is the two conductors end of your like current carrying coil, right? Now see this plane, this is our coil plane. The two side are the conductor side. I have drawn it here. You can see that this is the two side and this is our conductor coil plane, right? Now what about the MMF? If this is our flow of current, right, then the MMF would be or always be perpendicular to this plane. MMF would always be perpendicular to this plane, right? Now this MMF vector emanating from this plane will be placed across this coil axis. Here this is our coil. Due to poor lighting you may have problem in seeing this. This is our coil, this is the overhang. Okay, just a minute. So obviously if you consider this hollow actually this is not a hollow cylinder. In case of a rotary armature this will be a solid cylinder, but if we only want to consider the coil, you can see that this is our coil that we have placed, right? So this coil is means the two sides of the coils are as shown by these lines, and you can see that this is the coil, this is our means obviously this will be a hollow, means it is just a coil, not this, means the middle portion is not filled up with any material, and this is our overhang region, and these two forms the side of the coil. However, one thing that if you see that a current is flowing through this like if this is our, okay, let me show you that if this is our dot and this side is cross, right? So what you can expect that if this side cross means the current is flowing in this way. So if current is flowing in this way, what you will get? You will get the corkscrew rule. Applying corkscrew rule, you will find the magnetic lines of force is like this. Means if this pen tip indicate the magnetic lines of force arrow, then this is pointing in this direction, right? Pen tip is pointing in this direction. Similarly, this side, it is the outgoing end. That is why I have shown it by putting dot over here. So if this is carrying the outgoing current, then also you can find out the current using your corkscrew rule. So basically what you can see that both the conductors are means creating a current, sorry, a magnetic field that is trying to means penetrate through this one, right? So in a nutshell what we can say that armature MMF is always perpendicular to this plane. However, what about the magnitude of this one, and this we can always represent this perpendicular vector as a combination of one vector that is responsible obviously different current. Try to understand one more thing.
before I go back to that whiteboard mode, that this current will vary, and accordingly the magnitude of or the length of this plane will also vary. The length of this plane indicates the resultant armature strength or armature MMF strength that is perpendicular to your coil plane. However, when this armature vector, means if you consider, you will see in a nutshell what we can see, that these means the length of this plane, or the length means armature vector length, will also execute a sinusoidal motion. Although it is perpendicular to this plane, but it will also execute a sinusoidal motion, like sometimes it will be in this side, sometimes it will be in this side, because your current is alternating in nature. So armature MMF will sometimes be this side, sometimes will be this side. Now, and also of different magnitude. Now, if when your coils two sides are exactly suppose this my two fingers are indicating north pole and south pole, right? Now in that case, if your coil current at that same instant reach its maximum value, then you will get maximum armature MMF, and that will be purely cross magnetism, and this is expected because your unity power factor current induces cross magnetizing current. But when there will be some change, like suppose the current is having an angle 30 degree, lagging an angle 30 degree, so what we could expect, that this is the position when your coil will generate maximum EMF. But when we will turn the coil 30 degree like this, at that time the MMF will become maximum value. MMF will reach its maximum, but that MMF will also make an angle 30 degree with means this decomposition, with this decomposition that will make 30 degree angle. So that is interesting to note, that when your armature MMF will get its maximum value. So I hope this gives you certain means insight. Now we'll try to explain again in the whiteboard.
So hope that presentation gives you certain idea. So now let us draw a line that is having an angle psi, that angle of lag. Just a minute. Now see, here we are having this coil. So okay, before drawing any okay, we are having this coil. Now see what we can have. We can draw a line that is having an angle psi. What is this angle psi? Psi is the angle of lag. Why we have drawn psi in such a way, and what is its implication, that I will discuss later. But this is psi. Now how to understand this psi and how to draw it. Before I talk about psi, let us consider this MMF, the magnitude of this MMF that is perpendicular to your coil plane. Coil is carrying this current I theta, which is at an angle psi, means lagging the EMF at an angle psi, right? So how to understand that? If you have understand the demonstration that I was trying to show you with this paper strip and wire, this is the coil plane, right? This is the coil plane, and this is perpendicular to this. Now this magnitude of this mmf, if we at the moment we are considering the fundamental harmonics only without considering the any higher order harmonics, if we consider only the fundamental, then how to find out the magnitude of this one? What type of coil we are having here? So I hope you still remember that I discussed when we are having full pitch, this is full pitch coil, sorry. So in case of full pitch coil, what we can have a rectangular distribution like this, and if this one is A, that is given by your, so this total thing is what I am trying to say. Let me show you that yes, this one. Now see here, here we are having a case when it is rho by 2 is 0. We are considering a concentrated full pitch coil, so rho by 2 is 0. Now what we are having here, it is 4a pi by r. So if it is fundamental, then it will be 4a pi, 4a by pi. Now what is your a? A is npi. So in that analogy, what we can say that this bottle green arrow that indicates mmf, or the one which I was showing with my pen, that was the instantaneous value of mmf. That instantaneous mmf is 4 pi np, that is the number of turns per pole, into I. Small I is the instantaneous I. Now see that what we can expect, like if we consider how to make you understand that if we consider the current is 0, means current power factor, this psi is 0, when the current 0 means psi is 0, when the current power factor is 0, then exactly what we will get, that is, will be cross magnetizing in nature. And in that case, you can, obviously your coil is rotating in space, but you would have got
means at any time instance, had we considered a load with power factor 0, we can always find out. Obviously, we will have the same coil rotating, but we can always express two components of current, or rather two components of MMF. One is along this and another one is along this. These two are indicating what? This one, this perpendicular one, it is actually due to that demagnetizing effect. And another one is cross magnetizing. However, here interesting things to note that fortunately, unfortunately, our current is not in phase, rather it is lagging that one by psi. So when you are at an angle theta, basically your current should have a magnitude that is theta minus psi. The current magnitude should be theta minus psi. However, as psi is dependent on external load power factor, psi is not machine's internal, or psi is not dependent on space angle variation, we can constant psi is constant for a constant load. So what we can do is that instead of drawing or considering this white line as our datum line for this will obviously be datum line when psi is equal to 0 or your generator is supplying unity power factor load, but here it is not supplying unity power factor load. So what we are doing, we are considering a line, since this one will be basically that angle whatever be, it is always this. So for this we can assume that we are having like our datum line for current for this particular load is also lagging the original datum line by an angle psi. This is in clockwise direction. So with respect to this datum line, when you measure current, you will get always this angle is how much? This angle is theta minus psi, right? Now, if it is psi from this one, that geometric neutral axis, if this is psi degree means inclined to that, then obviously our this we will find a line, this line say AB, that is perpendicular to this pink dashed line. And what is this pink dashed line? This pink dashed line is acting like what you know as MNA for your DC machine. This MNA for DC machine is here, is that it is at an angle psi, and it is very easy for you to understand, because when your theta is equal to psi, your current is 0, and when armature current is 0, like what I am trying to say, when these conductors are here, if we consider conductor's position here, then these conductors will carry 0 current, because you can see that Im sin psi minus psi will become 0. So that is the 0 crossing for the conductor current, and whenever conductor current becomes 0, obviously you can consider that is your MNA. That point is your MNA, because conductor current is becoming 0. So in terms of current, that is your MNA. So from M&A, if you draw a line perpendicular to it, you will get a line that is responsible for cross magnetizing action for that particular, sorry, that M&A perpendicular to this, it is the demagnetizing or magnetizing line. Now we are developing two components. One is A11, another one is just perpendicular to it, A21, in such a way that their combination always gives us this capital A, which is 4 pi Ni. So what we can write, that A11 is equal to what? A11 is equal to A cos theta minus psi. How much is this angle? Try to understand by this geometry. This is 90 degree. So what is the angle in between these bottle green line and red line? That is 90 minus theta. Okay, and this pink line is making an angle psi with this red line, red dash line. This so therefore this much is how much angle is this? This angle is 90 minus theta minus psi, means actually plus psi, means what I am trying to say, it is this angle is 90 minus theta plus psi. So this is actually what? This is your omega t. Now this A11, this can be written as what? This A11 can be written as this cos of this total thing, like sorry here, yeah, this is 90. Just let us make it clear, otherwise it is causing confusion. Yeah. So this one is our capital A, that is 4 pi NPI. We are convinced with that. Now we want that projection of this A on this line. Now what is this line? This is 90 degree. And how much is this one? This line, they are making an angle psi. Now what is like, if this is psi, then see one more thing here, that this red line, red dashed line, and this white dashed line, they are 90 degree apart, right? And this white dashed line and this bottle green line, they are 90 degree apart. Now
as these two are 90 degree apart, so we can see that this red line and this bottle green line, which is perpendicular to this coil plane, this angle is how much? This is theta, and this angle is psi. So this one here, this angle is this much angle is theta minus psi. Now we would like to find out the if we form a right angle triangle. Here this angle is 90 degree and this angle is theta minus psi. So what we can write, A11, that is should be A cos theta minus psi. So A cos theta minus psi can be written like A is 4 by pi np small I cos omega t minus psi, and that is equal to 4 by pi np. This I can be replaced by Im sine here this value sine omega t minus psi into cos omega t minus psi. So this results in 2 by pi np Im sine 2 omega t minus 2 psi. Such a sweet expression, right? Now this one, this is the most pathetic case when I reach the end of the paper without money. Anyway, so we can write A21. A21 is this one, so it should be like this. Let us copy this one. So we'll do suitable manipulation. So now let us suitably alter it. It is A21 A sine theta minus psi. So this should be sine omega t minus psi. So then finally you will get it like now see the beauty that both component A1 and A21 they are varying with the frequency that is twice of your means electrical oscillation frequency. Here it is 2 omega t. I am not talking about 2 psi, I am talking about 2 omega t, and in the previous case also it was 2 omega t. So these are varying, but what is their average value? Their average value, see, if we write that A11 is the average value of all these A11 over a complete cycle, this gives us 0. But when we are talking about the other one, this gives us how much? If you take this, right? So what is the physical meaning of this constant average value? Physical meaning, where can you get this A21? What would be its like its phase or its angle? See, if I am interested in drawing this A21 in that previous diagram, it is clear that this A21 will be at an angle that I have already drawn, where this one, like, that A21 is, isn't this A21 is acting A21 average? Taking average means what? You make a complete cycle and then figure out what is its direction. Now A11 average is 0, but A21 average, it's having some value, and that is quite means it's interesting to note that A21 average is directed to which axis? To that virtual axis, or virtual means not virtual, rather that even a position or that data line of current, along that you are having A21 average. So that is very, very interesting. If you increase this power factor, your A21 average will shift. Now this A21 average and this A21 average constant means it is like whatever be your coil position, this A21 average you will always find it there. Isn't it very surprising, interesting? But can you just recall that how it resembles the idea of brush shift in a DC machine? That in case of a DC machine, if you want to neutralize means, or if you want to commute the coil in magnetic neutral plane, that you need to shift brush, and then that brush shift gives you this kind of angle psi, and accordingly you used to get some like some amount of demagnetizing current, some amount of cross magnetizing current. Now this A21 average, again, it is so beautiful that we can again have two components of this A21 average, or representing A21 average. One that is along our cross magnetizing direction,
that is A21 cos psi, and the another one is how much? That is along this axis. Now, obviously, this double frequency pulsation of A11, although average value of A11 is 0, but cannot be ignored because they cause an they induce a double frequency EMF at your conductors, but means it is like a small pulsating magnetic field. However, if you consider A21 average, that is a steady one. A21 average itself is a steady one, having a steady component, a steady demagnetizing action to weaken your field winding. That is given by A21 average sin psi, and one constant cross magnetizing one or transverse one, that is A21 cos psi. Now we will gradually move towards concentrated coil, this is concentrated winding, full pitch. So concentrated winding full pitch gives us this value 4 pi npi. Later on, if we make it distributed, we have to consider kb. If we do some short pitch or chording of the coil, then we need to consider Kr. So Kb and Kr we can introduce to figure out this A. Then from this A we can figure out the two components. One is A small 11. What is A small 11? A small 11 is a component that is the instantaneous component or instantaneous like if A is the MMF perpendicular to the coil plane, and let us assume that coil is at an angle theta and coil is carrying a current of this power factor angle psi, then this coil, this one like will cause this A, we can break it in two components. One is in like in line with AB. What is AB? AB is the perpendicular line drawn from the virtual MNA or that datum line for current I. So with respect to AB, we can find out one component, that is A11, and we can find out another component that is perpendicular to that AB or that is parallel to your virtual datum line. Then we find out average of A11 and A21 and have discovered that A11 over a complete rotation produce 0 average value. However, this A21 remain constant, and significantly it's or also interestingly we can say that A21 average is always directed along the datum line, as I have shown. So when it is always directed, then we can find out the two components, that is one is purely means cross magnetizing, that is A21 cos psi, another one is purely demagnetizing, that is A21 sin psi. Now we will want to consider the multiphase meshing. So for multiphase meshing, we will assume that balanced operation, obviously unbalanced operation will cause much more thought-provoking and intriguing analysis. We will keep it for your next semester. Hopefully next semester you will get to know more about this.
Now, see, now we will consider instead of one coil, let us consider two coils are here, means two phase winding. Uh, So obviously at certain instance when you are having uh, in this case your machine will have two EMF induced. One is say E1, that is at an angle theta, will be not two phase, let us write, we are considering M phase balanced machine. So what is interphase angle? That is 2 pi by M. Like in case of three phase machine, it is 2 pi by 3, so it is 2 pi by M. So for the same, when it is E1 theta, what should be the position of your E2? E2 coil should placed in such a way that E2 theta should give you and similarly if it is connected to a balanced load that is carrying I theta current in each phase at here theta is equal to omega t. So I1 theta is equal to Im. This phi is the power factor angle, that is load tan inverse, load reactive part by tan inverse load XL by RL, where your load ZL is equal to RL plus XL, JXL. Now, on another current I2 theta should be how you written I2 theta, since it is a balanced load, so I2 theta should also be following the nature of E2 theta, that is lagging I1 theta by an angle 2 pi by M. Now, now, oh, now let us try to understand them pictorially. So this is our S, this is N. Again draw the datum line. Again let us place the first phase coil 1 at here, that is at an angle theta. Now the second coil should be placed at an angle 2 pi by lagging 2 pi by m from the first coil. This is 2 pi by m, this angle gap. Now let us consider, let us draw that same psi line, because we are considering the same power factor. So from this line, this is the neutral line for current, where when the coil passes through this line, the first coil, its current becomes 0. This is the direction of rotation. Now So what we can write, like the first one here, let me copy this equation. So this is for A11. What you can write for A212? What is A12? Like the second one, the second phase we are considering, this is due to phase. So if it is A1M, so we can write it for A1M also. So when you will do it for A12, what you will get, like here, a change you need to introduce this. See, in case of A12, here one more factor will be there, that is minus 2 pi by m. However, I mistakenly deleted them. But if you consider, you can verify it that here also you will get, it will give you like, the second one will give you, yeah, if this is our A11, so what about the A12 coil? A12 coil, as it is 2 pi by m in this way, so obviously this would get it at, means if you draw neutral from for that one, then it will be at 2 pi plus 2 pi by m. So everywhere you will get a factor that is the same factor will be plus 2 pi by m factor you will get everywhere. Now see that why this A12, just a minute, here yeah, here I have made a slightest mistake, like the way we have shown it, the direction here, the second coil is cutting the flux lines first. So what we can see that, okay, so no, I think I have not made any mistake. Just let me draw. So whenever you will find yourself in confusion, a very simple way to draw the line that is perpendicular to your this second phase line. Let me use this blue color for second phase. So for blue color, what you will get, if this pink color is indicating the one, then for the second phase we can find out a line, say CD, that is at an angle 2 pi by m. So if this is 2 pi by m, now what we are trying to do, we are trying to figure out, now obviously one question that may comes in your mind, that now as we are having two coils, like previously it was one coil, now we are having two coils. So which coil to be considered here? Obviously when you are considering that first coil shown by white color, this one, then you have to draw a MMF, let us use that same bottle green color, that is perpendicular to this one, like this dashed line. This angle is 90 degree, and then you have to figure out that this much is again theta minus psi, where psi is your power factor angle, and you can figure out you can find out two components, one of which is A21, another one is A11. Now when you are having this blue one, like you are having the second coil, this is second coil, so for second coil you can actually for second coil you can also draw this kind of line, this neutral line, where the second coil current will become neutral. This blue line should be at an angle 2 pi by m from that psi line. So this is actually 2 pi by m plus psi from 0, if you consider it is 2 pi m plus psi line. So accordingly for this also you can have say this this cyan color that indicate the MMF that is perpendicular to this second coil. So MMF perpendicular to this second coil be like this A. So you can also figure out its two component. One is along this CD line and another one is perpendicular to this. However, interesting fact is that this A can also find a projection on this AB line. Only thing is that instead of considering whatever you have considered for AB, when you are taking projection for this one, this one is A, this one is A, magnitude wise both of them should be same, because the winding is balanced and A is that NPI, so magnitude wise both of them are same. But this bottle green A is perpendicular on the coil shown by this coil side, and the cyan MMF is perpendicular on this navy blue coil side. Now you can see that for bottle green you are going A11, that was like A cos theta minus psi. Now here as it is balanced, so the same projection for capital A on that same AB line is how much? You just need to consider another angle plus 2 pi by m, right? So if you consider it, then what you will get? You will get but instead of writing it A11, we have to write it A12, that is this contribution of second phase, that is 2 pi by m away from the first phase. So similarly A21, here you will have A22, and here you will get A sine theta minus psi plus 2 pi by m. So if you do that, you will find it will give you 2 pi np im 1 minus cos 2 omega t minus 2 psi plus 4 pi by m. So by similar analogy, we can write it like A1m A1m is equal to 2 pi npim sine 2 omega t minus 2 psi plus 2 m minus 1 by 2 pi m. And similarly A2m is equal to 2 pi npim 1 minus cos 2 omega t minus 2 psi plus 2 m minus 1 2 pi by m. Now we have to find out the grand one. Grand means the, like previously we find out A11 means A11 average and A21 average. Here we will find out A1 average, that is by summing all A11 plus A12 A1m. So this will give us what? 2 pi np im summation running from I is equal to m minus 1 by I equal to 1 because m minus 1 is here, so you can write it like this expression just. Generally we sometimes cause I as your current, so let's make it be K. Now you can see that over a complete average, if you take this one, will give you 0. So A1 average on a complete cycle is 0. So same for the multiphase one, sorry, the single phase one, that component remains 0 but has an effect on inducing double frequency EMF. Now you consider this. You will see that it will give you an average component. By writing similar way, you will get 2 pi. Here it is the beauty. You will get m for m number of phase, it will be n p I m. So this is very important equation, and from this A2 average you can write as we have written in the previous case that AD, the total demagnetizing effect is A21 average, sorry, A2 average sin psi, that is 2 by pi m n p I m sin psi ampere turn per pole, and Q cross magnetizing is A2 average cos psi 2 pi m n p I m cos psi ampere turn per pole. So here it is clear that we are getting this cross magnetizing and demagnetizing effect. In that our upcoming video we will discuss rotating magnetic field, but you please try to digest and assimilate all this well. So good luck.